to pathways to sustainability. And can you hear me okay? Good? Too loud? Too soft? Okay. So today, we know there's a lot of noise and activities towards renewables or sustainability, and there's different ways we might get there. There's questions whether we can get there, and so I think this is a very talented panel talking about some of the pathways that might help bring us to this sustainability future that we're all looking towards. So we're going to be doing a little bit with nuclear, a little bit with natural gas, and a little bit with natural gas, sorry, and a little bit with combined capture and use, combined capture, use, carbon capture, use, and sustainability. And we'll be going in that order. And I will introduce the panelists as we go along, I think. And they have a full bio, so I'll just mention a very little bit about how talented my fellow panelists here are. So we'll start talking about nuclear. And so Dr. Shannon Bragg-Sitton has a PhD in nuclear engineering from the University of Michigan. And she has some other degrees, which I'll let you check with her bios. And she is the lead for integrated energy systems at the Idaho National Lab. And she's been in a lead with a number of projects with the Department of Energy. So she's quite a well-respected person in nuclear. And so I'll turn the floor over to her.
Well, thank you so much, and thank you for the opportunity to speak to this group. This is the first time I've been to this conference, and I hope to bring a new message to you. I'm expecting some of you may know some things about nuclear technology and innovation that's been going on in the space. Others, it may be fairly new. And so I'd like to just open your minds to think about how we might imagine future energy systems where nuclear technologies play a significant role and why they should play a significant role. As we've talked about in other sessions here in this particular conference, the projected increase in world energy use by the U.S. Energy Information Administration is quite significant. It's expected to increase by about 28% by the year 2040, with most of this growth being in non-OECD countries. About 60% of the electricity demand increase expected to be in non-OECD countries. If we don't change the way that we produce that energy, it's not just electricity, but energy in general, then that will correspond to about a 2.7 degree increase in temperature. This, of course, has significant environmental impacts, potential food shortages, severe wildfires, mass coral reef die-offs, a lot of things that we should be concerned about. If we look to the literature and articles that have been coming out over the past couple of years, we see more and more pointing to the potential role of nuclear energy in preventing some of these dramatic changes. I've just highlighted a few here on this slide. I know those are going to be a little bit difficult for you to read in this large room, but I'd be happy to share these afterward. We've been talking about the shift from renewable portfolio standards to clean energy standards and incentives. We've also heard yesterday about some of the initiatives that Excel Energy, which serves this region, has put into place. And by the year 2050, they are seeking to have 100% carbon-free electricity from Excel. And they specifically note that carbon-free does not just include renewables, but it also includes both advanced nuclear power plants and fossil fuel power plants with carbon capture and sequestration. So they are leading this charge, and we should consider why and take a look at how this might come to play. So just to familiarize you a little bit with nuclear energy, nuclear power is one of America's largest and most reliable domestic sources of clean energy. In 2018, nuclear energy provided 55% of the emission-free electricity in the United States. This is significant. We need to make sure that we maintain that carbon-free electricity on the grid as we look to how to even further decarbonize our grid. Nuclear also boasts a pretty respectable capacity factor, having a fleet-wide average of 92.6% here in the US. That's unparalleled. So we need to think about how do we keep nuclear energy competitive and make sure that it continues to serve in this significant role. In 2018, MIT updated a study that they conducted on the future of nuclear energy. This particular study had a number of contributors from around the industry as well as more broadly from the energy community. And I think there's some significant outcomes from this study that we should consider as we look to the future of our energy systems. As we all know, the world faces challenges of reducing emissions of greenhouse gases while simultaneously expanding energy access and economic opportunities to billions of people that currently don't have access to electricity, clean water, and other resources that we utilize every day. And there's a number of solutions that we can look at, a variety of low or zero carbon technologies that can be employed. But as I'll show you on the next slide, this study pointed out that without the contribution from nuclear energy, the cost of achieving these deep decarbonization targets increases significantly. As the cost of nuclear comes down, the contribution of nuclear anticipated in these portfolios is expected to increase dramatically. So we'll ask the key question, if this is the case, why isn't nuclear thriving? And what can we do such that it does thrive? Well, the three things I'll talk about is the fundamental problem being cost. I won't argue with you, nuclear is expensive right now, so let's talk a little bit about why. Public concern and energy policies. So first, let's look at this. It's very difficult to see in this room, I apologize. This is just a quick summary of some of the outcomes from that particular study. The orange bars on the left, what you see is the average cost of generation, total system cost of electricity. The orange bars represent a no nuclear scenario, zero nuclear being added. The center one, the blue, represents a nominal cost for nuclear energy, and that cost changes for the two different regions shown on this summary. And on the right, the yellow bar represents a low-cost nuclear scenario. As we look along the x-axis, that's the emissions limit, where 500 grams of CO2 per kilowatt hour is currently the world average emissions. As we move to the right on that, going down to 10 grams and then 1 gram, we see that contribution of nuclear increasing. If we look at the nuclear contribution over on the right-hand plots, and on the left, we see the system cost increasing dramatically if nuclear is not a part of that. So I encourage you to take a look at that study and understand all the implications of that and how that plays into these results. But let's talk about how we address these challenges. The first one and the largest contributor to this is cost. How do we reduce the cost of new nuclear plant builds? We need to focus on using proven project construction management practices that will increase the probability of success. So what all does that entail? If I look at the Vogtle plant that's currently being built in the southeast US, when that plant was started, the construction for that plant was started, I think it was on average about 50% complete in its design. We've got to change that equation. Plant design needs to be much closer to 100% complete before construction starts to avoid some of the small changes that can lead to significant delays and regulatory review through that process. And the longer it takes to construct, the more costs build up. We also need to look at the supply chain and using a skilled workforce, making sure that supply chain is in place in advance of construction. We need to include manufacturers and builders early in the design process to make sure that the systems that we are designing can be constructed efficiently and that they can meet relevant standards for those components. We also need to identify a primary construction manager that has proven expertise in working with multiple independent subcontractors. These are challenging projects requiring a number of different workers, so we need to make sure that we have the right skill sets in place. And we need to make sure that all those contracting bodies have a vested interest in the success of that project, that they want to get to completion just as much as the next contractor. And we need a flexible regulatory environment. We know that as we go through large projects, small changes will occur. We learn things as we go. Small changes occur. We need to make sure that those are not changes that represent significant stalls in the process. So that regulatory environment needs to be able to accommodate small changes throughout that process in a timely fashion. Moving to the next item, we need to shift away from the way that we've constructed large-scale nuclear plants in the past. Most of you, if you think about a nuclear plant, you think about a very large-scale system, off in the distance, producing huge amounts of electricity for a centralized grid. Gigawatt-scale plants. Those are often very site-specific, designed specifically to the site. And in the US, every plant pretty much is a unique installation. That drives up cost. So we need to move from that type of approach to plants that can be made in a serial manufacturing approach and standardization of plant designs. And we'll talk about how that's happening now. The second area was public concerns on potential consequences of severe accidents. Severe accidents have an extremely low probability of occurring, but a high visibility if they do occur. So the industry has worked towards shifting to designs that incorporate extensive inherent and passive safety features. In those designs, this design evolution has already occurred in many of these reactor designs in Gen 3 light water reactors, and is exhibited in plants built in China, in Russia, and the United States. These passive designs can decrease the probability of an accident occurring, but then also mitigate any consequences if those accidents were to occur. We also need to look at modifications to the regulatory framework that improves efficiency and efficacy of licensing reviews. In the policy space, we need to think about policies that look at the end goal. What is our goal for technology assets? We want technologies that minimize emissions. We want technologies that are reliable and resilient. So we need to look at policies that reward market value and what they bring to the market, as opposed to selecting technologies in advance. We see this motion in a lot of places that look at clean energy standards as opposed to renewable standards. But we need to look at the merits of those technologies, and this can dramatically change investments. If policy forecloses the role of nuclear from the outset, we can't expect to see investment in that technology as we move forward. And this can significantly delay the this can significantly delay our progress toward climate change mitigation and may increase the cost ultimately of deep decarbonization. So let's talk about some of the areas of innovative research and innovative design that's happening in nuclear space, and some of the investments that's coming from the government area to help support increasing the rate of adoption of these innovative technologies. So advanced reactors, as I said, most of our plants right now are very large scale, gigawatt scale plants. And in the United States, they're all cooled by light water. 2/3 of these are pressurized water reactors, about 1/3 boiling water reactors. If we look to what's happening in the advanced reactor development space, we see more than 50 different companies right now developing advanced reactor designs. That's significant. This is more than we've seen in a very long time. There's interest and there's need. These range in size from very small systems on the order of a megawatt to medium scale systems, maybe 20 megawatts to 300 megawatts, to large scale systems, something much more akin to what we see in operation today. And I'll talk a little bit about how those help to address some of the challenges that I just spoke to. The reactor types are also quite different. Most of those pushing to much higher temperature operations that increase the efficiency of power production, as well as allowing high quality heat to go into industry and the production of other commodities such as hydrogen that can go into fuel cell vehicles or into the production of synfuels. Overall, these advanced reactors provide enhanced safety. They can support versatile applications. Many of them can process waste streams or use nuclear fuel from other reactors, reducing that footprint from the nuclear area. And many of them burn even longer so that they reduce their own waste streams as well. And many are taking the approach of using advanced manufacturing techniques in order to reduce costs of these technologies and begin moving toward that standardization need that will further reduce cost. In the area of small modular reactors, these systems are designed to be exactly that, modular in the approach. This introduces a new business model in which the capital investment to start that plant operating is much smaller. We might have a unit that's 50 or 60 megawatts, but a full plant might entail 12 modules, where each module can be added to the plant as it's needed by that facility. So you don't go quite as deep in the capital investment from the outset, and construction time is also dramatically reduced from about 8 years or so for a large-scale plant down to 3 years to get that plant up and running. This also opens up a number of siting options. Many of these are sited below grade and introduce seismic isolation. And they're designed for flexible implementations, such that they may produce electricity for some regions. They may use heat to support hydrogen production or chemical processing, or using what's typically waste heat for district heating, things like that. And I should point out also, it's very difficult to see here, the footprint of a large-scale reactor is about 1,500 acres for the current fleet plants. And they also include about a 10-mile emergency planning zone. If we move to a small modular reactor, the footprint reduces down to about 50 acres and an emergency planning zone of less than 0.2 of a mile. Keeping that in mind, you can begin to see how these can be now sited closer to the end use, closer to municipalities, closer to factories that might be utilizing that energy. NuScale Power is in the process of developing the first small modular reactor for implementation here in the US. They are undergoing design certification right now with the Nuclear Regulatory Commission. And they have fully embraced this factory manufacturing approach with shipment to site of each of those modules using truck or rail and allowing for very rapid on-site installation of these systems. Microreactors take this even further. Where microreactors are very small in size, the footprint of these reactors is less than an acre. The emergency planning zone, again, much smaller than what would be required for a standard system, likely much smaller even than the small modular reactors. They also embrace simple designs. And what I mean by this is self-regulating, such that we can adopt semi-autonomous or autonomous operating modes so that these reactors now don't have near the same type of requirement for on-site operators as we do for large-scale plants. And they can accommodate the needs of a microgrid much more readily by having an inherently responsive system. In that way, they can provide energy to many remote locations that are currently served by diesel generators that are reliant on limited time frame fuel supplies, whereas most of these systems have a much longer fuel cycle that might be 2 years, 5 years, even 10 years in some of these designs. So they have on-site reliable fuel supply for a very long time. They are designed to be factory fabricated and in some cases fueled in factory, where all that has to be done is ship those to site via truck, rail, barge, even a plane, connect the power conversion system, and you're good to go. So these offer a completely new opportunity for reactor technologies. There's also innovation going on in current fleet plants. So advanced fuels. Nuclear fuel has not been the same from the onset of the technology to what it is today. Many of these changes have been very small, but they've enhanced the power density, they've enhanced the fuel cycle length in each of these plants. And now we've been developing for a number of years accident-tolerant fuels, also referred to as advanced technology fuels, that allow the fuels in these reactors to withstand beyond design basis events, extremely severe accidents for a much longer period of time, where if we had a full loss of cooling event, there would be a much longer coping time to bring in additional coolant. Some of these designs, some of the small modular reactor designs, are designed to operate for many days without cooling, and accident-tolerant fuels can be a big part of that as well. Many of these fuels are currently in test in commercial fleet reactors to develop the data necessary to license them for a full plant reload. This has been a significant effort in the US, as well as a collaborative effort with many countries around the world. Integrated energy systems is also another opportunity that we want to consider. I'm probably running out of time. I'll try to speed this up a little bit. Integrated energy systems look at how do we better utilize all of our assets? How do we better utilize nuclear technology and the assets it brings to the table, dispatchability, high power density, renewable energy with fuel costs of zero, fossil energy with its reliability that is brought to the table. How do we best utilize these in each of these scenarios, not just to produce electricity, but also to support the heat and energy needs of industrial applications, to support the production of clean water, and to provide transportation fuels or electricity to transport in ways that best utilizes each of these assets. So maximizing the contribution of these low carbon energy generation technologies across the energy use sectors, but then also supporting a resilient grid and converting valuable resources to higher value products. Taking those carbon resources that we are so rich in here in the US, and instead of burning those for heat and electricity, can we use those and convert them to higher value products? So let's best utilize the resources that we have. So this is a new paradigm for nuclear energy, where traditionally we've just produced electricity. But now we look at what can we produce on the right side of this? How do we get to that efficiently? How do we make sure we don't throw away energy, but we utilize it to produce the products that we utilize each day? I'm going to point you to a couple of reports that were just recently released on how we might utilize existing fleet reactors for the production of hydrogen and for the production of clean water. I won't go through the details here, but just enough to say that it's very promising. We've seen some very positive results. These reports are available for download. The water study will be released here very soon. And on the right side, we see the results of that. And those are two significant awards that offer private and public partnership combined with combined investment to demonstrate these technologies at current fleet plants. One led by Exelon, and the other via a multi-utility consortium with First Energy, Xcel, and Arizona Public Services. I'm going to skip over this example because I think I probably don't have time for that, but I will. Oh, I have 2 minutes. Well, let's talk about it a little bit then. I chose this example here. We're doing a lot of work in hydrogen production. And how do we inject clean energy into hydrogen production for fuel cell vehicles, for ammonia and fertilizer production, for steel manufacturing? But how do we also utilize that hydrogen in combination with captured CO2? Can we do that and produce synfuels that now are either a net zero carbon, or in some cases, depending on how we look at the processes, carbon negative? And so by looking at the assets that come to the table across the technologies, we can begin to look at this instead of in our individual technology stovepipes. We can start looking at it more holistically. We'll talk a little bit more about these collaborations in the government session tomorrow morning, where you'll hear from multiple laboratories and what we're doing together to look at what each of the applied energy laboratories does best and how do we do it even better together. So I do want to leave you with the thought of what the future might entail for nuclear. We're used to the isolated plant on the hill. What if we use that for remote villages in the Arctic regions to work with wind and with solar to supply reliable, resilient energy for a remote fishing village, and to provide heat to a greenhouse so they have vegetables year-round? What if we use a small modular reactor to support an industrial facility and take advantage of that reduced emergency planning zone and site it very close to the city, which is very attractive from a jobs perspective and a product movement perspective? Or perhaps we can open up new regions by processing seawater, or in the case of Arizona, processing brackish groundwater that they have to pump and get rid of anyway, to provide for plant cooling needs as well as municipal needs. And this is my final slide. I was happy to be a part of a project this year with the Clean Energy Ministerial and a relatively new initiative called Nuclear Innovation, Clean Energy Future. The Breakthroughs book has a series of vignettes on all of these technology innovation areas for nuclear energy. This was put together by the US, Canada, and Japan, which are co-founders of this particular initiative, and it's supported by a number of other countries as well. This is a coffee table book. It should pique your interest. and then dive into the references, dive into those resources to learn more about the technical capability and the economic capabilities. And with that, that's all I've got. Thank you.
Perfect timing. So I'm convinced, and I hope you are too. Okay, so next we're going to move on to natural gas and see if there's going to be a dash to gas, and if the shale gale will continue. And so we're going to move to ExxonMobil. And so Sarah Banasak, who has her master's from, which one? University of Hawaii, right, in applied economics. And she has an impressive decades of experience in energy, a lot of it focused on natural gas. And she's looked at this as from policy point of view, from a consultant point of view, from a corporate point of view. So I'm quite excited to see what she tells us about natural gas today. Oh, and we're going to hold all the questions to the end and then come back. So write them down, keep in mind.
Okay, thank you. Thanks, Carol. So good afternoon, everybody. I am, as Carol said, going to talk about natural gas. I will use some materials from ExxonMobil, but in order to help me be fully free in our discussion section, just understand that the views here are my own. Let's see, there we go. Oops. And I can't promise I'll be as perfect on timing, so you'll love this. Well, I know you will. Okay, so we talk often, and maybe in slightly different paradigms or frameworks, but about a kind of a dual challenge. We want to meet the world's energy demand, and we want to do it in a way that reduces environmental impacts and addresses the risks of climate change. So I think actually that this century in a lot of ways will be defined by how well we actually achieve that. And clearly this has been a theme throughout the conference in many different sessions as well as this panel. So I plan to talk primarily about how natural gas is going to fit into the future energy mix in a global context. But first, what I'd like to do is mention the work of my colleague who spoke quite directly to the role for natural gas in the US context. And this was just published a couple years ago. It was published in Energy Policy in 2017. My colleague is Brian Mignon. I don't know if any of the co-authors are here at the conference or here today. But this paper, as I said, it was focused on the US. And what they were essentially trying to do is answer the question about natural gas investments and whether they would be stranded in a carbon-constraining world. So what they did is they built off of the NEMS model, the EIA's NEMS model, and they used the 2017 AEO reference to build their base case. The 2017 AEO had the Clean Power Plan incorporated into it as policy. So what you're looking at on this chart is the changes in electricity in 2050 compared to 2015 for two different cases. On the left-hand side is a capped price case, a capped carbon price case, which the carbon price plateaus in 2030. And then on the right-hand side is a rising carbon price case where the price of carbon continues to climb after 2030. And then on the upper two graphs, what you have is generation by fuel, and on the lower two graphs, what you have is capacity by fuel. So they were using the cap price case to proxy an environment of not expecting carbon prices to continue rising, and particularly because this is a perfect foresight model. So what you see here with natural gas combined cycle being represented in the red sections of these bars is that both deployment, generation, and generation increase over time in either case, and therefore appear to be robust even if you have a late horizon rising carbon price. And then the new natural gas combined cycle capacity is not stranded, it's, even if the carbon prices are rising faster than expected. These results in their paper hold for a plausible range of both carbon price and natural gas price trajectories. So I think that's interesting. What you do see is on the rising price case, you do see a drop-off in that amount generated under the rising price case, but the capacity is still added and is not considered stranded. So I'll turn now more to talk about the global context for natural gas. This chart shows you the energy mix in 2040 for a variety of different models that are focused on climate stabilization scenarios. This is the work coordinated by the Energy Modeling Forum number 27 at Stanford University, and it provides a perspective on hypothetical 2-degree models. So what these results suggest is that predicting absolute 2040 energy demand levels in total or by energy type carries some uncertainty. You can see the variety in the heights of these bars and the different fuel mixtures for all of these different models. With particular models are likely heavily influenced by technology and policy assumptions. The differences in these models help put in perspective the uncertainty in the pace and breadth of changes in the global energy landscape that we're going to see. For comparison purposes, on the far left, the chart also includes energy demand projections in 2040 based on the International Energy Agency, IEA's Sustainable Development Scenario, or SDS, which was published in 2018 as part of the World Energy Outlook. The IEA specifically describes this SDS scenario as having global CO2 emissions that are fully in line with the trajectory required to meet the Paris Agreement on climate change. And just as a side note, IEA's other policy scenario in this World Energy Outlook was their new policy scenario. That scenario looked at emissions that were in line with the commitments made by countries. And the SDS emissions were about 50% lower than the new policies scenario where they're just meeting their announced commitments so far. So the assessed 2-degree scenarios on this page produce a variety of views on the potential impacts of global energy demand and supply mix. But with natural gas depicted in the red and in the pink, the continuing role for natural gas is clear. Nuclear is depicted in the dark blue, also with a continuing role. And then you can see the CCS technologies called out for gas, for oil, and for coal. So interestingly, even in a more recent scenario, the Bloomberg New Energy Outlook of 2019, gas power still grows by 0.6% per year all the way out to 2050. In the Bloomberg scenario, gas is used primarily for system backup and flexibility rather than bulk electricity, but in that scenario, gas generating capacity is still doubling by 2050. So the Energy Modeling Forum 27, EMF 27 full technology models provide a range of possible growth rates for each type of energy. And what we did here is simply take those implied growth rates and map them on a chart. So the red diamond here shows the average of the growth rates across the models by fuel type. Natural gas, which is in the middle, is on average projected to increase by these models at about 0.9% per year. Recall that Bloomberg New Energy was 0.6% per year out to 2050. So oil demand here is projected on average to decline about 0.4%. That's the second from the left. And together the share of oil and gas in energy demand is projected on average to still be more than 40% in 2040. And again, these are for scenarios that are meeting a 2-degree constraint. The projected growth for renewables and nuclear are quite strong. Renewables, hydro, wind, solar averages 4.5% per year, nuclear about 3% per year. So not on this chart is the carbon capture and storage, obviously a key technology for addressing CO2 emissions. Its projected share of energy demand also shows strong growth in these EMF scenarios. The key point here is that all energy sources remain important across all of these assessed scenarios. Though the mix of energy and technology shifts over time, oil and natural gas remain important sources of energy. Natural gas demand grows on average due to its many advantages, including lower GHG emissions compared to coal. The low side of these energy growth rates for the models is also shown, obviously, at the bottom of the range of the distribution. And in that case, the low side for natural gas across these models was a decline of 0.8% per year. Even in this extreme, though, gas remains part of the energy mix all the way out to 2040. Briefly, as an aside, and I think if you're in the energy investment session happening right now, this slide may also be shown. The point that natural gas is needed in the future energy mix, even in 2-degree scenarios, it's important to recognize that that also means continuing investments to meet energy demand. So what these charts show are the natural decline rates for existing producing fields for both oil and gas. Gas is on the right in red, oil on the left in green. So clearly, and then on the right-hand side of each of these charts, again, those growth rates from those EMF modeling scenarios are depicted in those diamonds. So at the top, you see the high demand growth, average demand, and then the low demand across those models that were projected. So you can see that the decline rate for natural gas, if left without further investment, would fall even below the low demand for natural gas across those 2-degree scenario models. So what we learn from this is that we do need continued investment in natural gas and oil, even in 2-degree scenarios. The reason for these additional lines is to show sensitivity. So each of these lines shows an additional year of investment, and then the decline that also happens with new investment. So we go invest in a new field. The new field is also going to have a decline rate. So if we were to invest only for 5 more years in natural gas, we would still be falling short of the lowest demand for natural gas predicted by that range of 2-degree scenario models that I had shown you. The IEA's 2018 World Energy Outlook estimates that significant oil and gas investment is needed to reach any range of scenarios out to 2040. Their estimate is about $13 trillion of needed investment in natural gas for their sustainable development scenario and $21 trillion for their new policies scenario. So the forecast and the role for natural gas is in meeting energy demand is most heavily built on its use for electricity. The bar chart here is based on ExxonMobil's outlook for energy, our 2019 outlook for energy. So to connect this ExxonMobil forecast with what we were just discussing in terms of the EMF scenarios, you can see on the right-hand side a graph of the emissions projected by the EMF 27 scenarios. So the downward sloping lines are the 2-degree scenarios. The blue line in the center would be the 2019 outlook for energy, and then the upward sloping lines are the EMF base case scenarios without the 2-degree compliance. So the mix of electricity going over to the left-hand side will vary geographically as a result of technology costs, domestic resource availability, and policy targets, including renewable portfolio standards for electricity generation. Much of the world continues to shift to lower carbon sources for electricity generation, wind and solar, natural gas and nuclear, based on local opportunities and policies. Note that China, which obviously is the tallest bar on the electricity generation graph, coal-fired electricity remains nearly constant to 2040. So the left-hand bar is 2017, the right-hand bar is 2040 in each pair. Its share in power generation decreases, the coal share in power generation decreases as renewables and nuclear provide almost 85% of the delivered electricity growth. The share of electricity used in transportation today is quite small, but it is expected to grow with increasing penetration of electricity vehicles as a result of emissions and fuel economy targets and cheaper batteries. ExxonMobil's outlook for energy explores this pretty extensively, and if you're interested, I encourage you to take a look. Just go to our website and go for Outlook for Energy. We have some sensitivities about moving fleets over to electricity. So the available supply of natural gas is relevant to its role in the future energy mix. The big donuts are showing you the proven reserves and their growth over time in 1995, 2005, and 2015. Proven reserves are influenced by demand levels. If there's no need, if there's no consumption of natural gas, the industry would not be proving reserves. If you, these are reported in trillion cubic meters. For 2015, that's equating to about 6,600 trillion cubic feet of proven natural gas reserves. On the total resource availability plane, global estimates are a little bit harder to come by. USGS did an estimate of global conventional gas in 2012. They estimated about 5,500 trillion cubic feet of natural gas. And then what's also very useful is EIA's 2015 estimate of global shale gas, where they estimated about 7,000 trillion cubic feet of technically recoverable shale gas, and then 33,000 TCF of risk gas in place. That work, incidentally, put out by EIA was put together by Advanced Resources International and Velo Kuskra, who spoke here earlier. I didn't include any supply curves on natural gas, and I don't have a readily available global one for you, but there were just a few years back quite a lot of very public supply curves for US natural gas. Most of them show about 1,500 trillion cubic feet, 1,500 trillion cubic feet available at under $5 per million BTU. So the regional diversity in supply and the trends in economics of trade will be important to the role that natural gas plays into the future. This is another ExxonMobil chart. It's showing you gas supply by region. The bars are for the year 2000, 2017, 2025, and 2040. And then the black square shows total production. So where the black square is above what's being consumed, you will have exports. And obviously where the black square is below the top part of the bar, you're having natural gas imports. Asia's on the far right, North America's on the far left. So for 2017, Asia Pacific's natural gas imports rivaled Europe's. By 2025, the region's total natural gas demand will likely surpass North America's. And in 2040, LNG trade is expected to meet nearly half of Asia Pacific's natural gas demand. This aligns well with a couple other forecasts I've heard here at the conference the last couple days. And then Russia and Caspian in the Middle East are in from the right-hand side. The Middle East is the first to the left of Asia Pacific, and then Russia, Caspian beyond that. So these are also anticipated to retain more than half of the interregional gas trade as significant exporters by further investing in export projects. And they're well positioned to do that. Before I close, let me touch briefly on questions about methane leakage and natural gas production, methane leakage into the atmosphere, because it's been brought forth as a relevant factor to the role natural gas will play in the energy mix in the future. I have to warn you, though, I'm not an expert on this whatsoever. I found the chart, and I'm here to show it to you, but if you ask me questions, I might be stumped. This slide gives you a picture of all the complicated dynamics for the global methane budget, what's going into the atmosphere and how it's getting sunk back out. But it's a reflection of a lot of hard work by a lot of climate scientists to develop this for methane as they have for carbon dioxide. In this case, if it's hard to see, on the far left are the two most prominent anthropogenic sources of methane. The far left is fossil fuel production and use, oil, gas, coal, about 105 million tons per year average over 2003 to 2012 period. And then you can see agriculture and waste next to the right at 188. So what's important here is that our ability to control methane emissions is in the anthropogenic sources. And this is one of the most efficient ways that we can reduce those important greenhouse gases. This is a chart from IEA that estimates how coal and gas might compare globally on total GHG emissions. The vertical axis is showing you methane emissions. So the purple shows you where gas is more competitive to coal, and then the darker color shows you where coal is better than the gas. There's a dotted line across just below 2%. It's roughly about 1.7%. That's what IEA estimated to be the average methane emission intensity for natural gas on a global basis. Of course, as the industry works to reduce methane emissions in its operations, that line would fall further down. On the right-hand side, on the x-axis, those are the conversion factors for converting methane to be GHG equivalent, so the global warming potential factors. If you're interested in whether or not you should be looking at the wider blue bar or the narrow blue bar, I would encourage you to, again, look up the work of my colleague Brian Mignon. In 2019, they published a paper, September 2019, in Climate Change Online. It has a very in-depth discussion of these global warming potential factors and why you might choose one over the other. But IEA said it correctly in their outlook in that when it comes to reducing oil and gas methane emissions, that is one of the most efficient ways to reduce greenhouse gas emissions overall. So finally, I started out by referencing the dual challenge of delivering energy while reducing environmental impact. And I like this chart because it emphasizes the magnitude of that challenge. Society's progress is intrinsically related to energy. If access to safe, reliable, and affordable energy is a critical enabler of reaching higher living standards, including better health care and a longer, healthier life. So what we have here on the y-axis, the vertical axis, is the UN Human Development Index. It's a summary of average achievement on 3 key dimensions: healthy life, intellectual skills and development through education, and then standard of living. And then energy is plotted on the x-axis. So not surprisingly, countries' HDI, or Human Development Index, show strong positive correlation to energy use. Access to energy obviously impacts people's lives in many positive ways. Today, a significant portion of the global population still faces serious challenges in accessing energy. And that challenge becomes even greater when you consider that by 2040, our global population will grow to 9.2 billion from 7.5 billion today. Almost 50% of the global population lives in countries that rank low to medium on the UN Human Development Index. They're all encapsulated in that box in the lower left. So advancing development for nearly half the world's population creates a challenge of significant global energy growth. And so that's why I think today's panel is important. We have to look beyond renewables. We're going to need as many ways of accessing cleaner energy as possible. To be realistic, the 3 factors that we've talked about or are talking about here today in terms of nuclear, CCS, and natural gas will not be the whole story. We can expect further technological advances. They'll be important too, to think about what some of them might be: batteries, chemical storage, hydrogen, low carbon industrial processes, advanced, less carbon intensive materials for building and infrastructure. These will integrate with nuclear energy, with CCS, and with natural gas to lift all the 50% of the world's population in this red square up on that Human Development Index. Thank you.